Welcome to Pavinars, webinars for the pavement community. Today we'll briefly talk about the long-term asphalt mixture aging as written in NCHRP Report 973. The first objective of this project was to refine the lab aging procedure. The current long-term aging procedure for asphalt mixtures can be found in AASHTO R30, and it's where you take a compacted sample and you age it for 5 days at 85 degrees Celsius in an oven. There are some limitations to this procedure, however. For example, there's no adjustment for local climate. The compacted sample does obtain oxidation gradients within the sample, so it's more oxidized on the outside of the sample and less oxidized as you move into the sample. And it's not representative of oxidation in the field, which is highest at the surface of the pavement and lowest toward the bottom of the pavement. Therefore, the proposed long-term aging procedure is a loose mix aging procedure at 95 degrees Celsius for anywhere from 0 to 32 days. And they can simulate 6 millimeter, 20 millimeter, and 30 millimeter pavement depth and aging of 4, 8, and 16 years. So for example, in this figure, this represents 16 years of aging at a 6 millimeter depth, and you can see, depending on where you are in the United States, you age the sample anywhere from 0 days all the way up to 32 days. The second and third objective was to calibrate PAM and estimate the inputs for PAM. PAM stands for the Pavement Aging Model, and it was designed to predict changes in the asphalt binder rheology when it ages. Originally, the PAM model was calibrated with virgin materials and cores from 8 sites. However, they looked at limited mixtures and they only had 1 core each, so there's no replicates. They didn't look at any warm mix asphalt, reclaimed asphalt pavement, or any polymer modified mixtures, and they did not explore the impact of air voids, asphalt content, the depth of the pavement, or any sort of aging. So in this research, they developed some new models and new equations. You can see here an example of one of the models, the kinetic model. And you can see there's various inputs, including G star and some constants and other inputs. But what they did is they developed additional equations where G star can be adjusted for depth, time, and the actual asphalt content. And so these revised equations and enhanced mixture and binder aging procedures were used to better estimate the inputs into PAM. Finally, the fourth task was to relate mixture aging to binder aging. So what they did is they aged both the mixtures and the binders together using the same regimen. They tried to correlate test results between those aged mixtures and the aged binders, and they conducted simulations of the evolving mixture properties over time. And what this did, it allowed them to develop a framework to predict changes in linear viscoelastic properties and to predict changes in fatigue properties. And you can see an example here of how they looked at both the G star of the asphalt binder and the dynamic modulus of the E star master curve. They also looked at the cyclic fatigue test, and they combined those together in order to have a pavement performance prediction simulation. And these are all inputs for what they called the Asphalt Mixture Aging Cracking Model, or AMAC. And this AMAC model and FlexPave, a software available, was modified to incorporate material property changes due to aging. If you're interested in learning more, I encourage you to download free of charge the NCHRP Report 573, and you can Google NCHRP Report 573 or the title, and the full citation is also listed in the box.